We present simple modeling, a normal sketch-based system for assisting amateur users to create desired animal-morphic heads easily. Creating visually reasonable 3D characters has always been a fundamental task in the modern game, film, and social media industries. Articulated animal-morphic characters, specifically their head shapes, are highly demanded and play an important role in 3D character design. How to quickly create human heads has been researched for a long time, but few works have focused on how to quickly create animal-like heads due to their rich shape diversity and rich geometric details. There are various traditional commercialized softwares for modeling animal-like heads, such as Maya and ZBrush. However, these softwares require users to possess considerable expertise and manipulate lots of complex tools in 3D modeling, which is labor-intensive and time-consuming, thus hindering the most novice users from instantiating their creative ideals. Unlike traditional interactive modeling pipelines, sketch-based modeling enables amateurs to get involved in 3D modeling in an easy and intuitive way. The research in sketch-based modeling can date back to the last century. As a seminal work of sketch-based modeling, TEDdy introduced a real-time, interactive method for constructing 3D shapes from input sketches. FiberMesh aims to model free-form surfaces from a collection of 3D curves, and these 3D curves would serve as handles for further shape editing. However, these traditional sketch-based modeling systems are based only on surface optimization methods, which would result in over-smooth shapes and lack of details. In the past few years, 3D deep learning has become an option for shape analysis and reconstruction. Thanks to the recent advance in 3D deep learning and rich datasets on human faces, such as 3D-MM and Face Warehouse, Deep Sketch-to-Face proposed an intuitive sketch modeling system for modeling human faces with diversified shapes and exaggerated expressions. But their system is limited to the parametric human face space. Due to the rich shape diversity over animal heads, parametrizing animalmorphic heads into a low-dimensional space is very hard. To address this, Sunny had introduced a view surface collaborative mesh generative network to enhance geometric details, but it does not support accurate control of global shapes, and it's also hard to generate reasonable geometric details. Another limitation of deep learning-based animal-morphic heads modeling is the lack of datasets. To address these problems, our key idea is as follows: to depict rich shape diversity and rich geometric details of animal-morphic head. As seen from the figure in the middle, we separate coarse shapes design and geometric details specification into two stages, and respectively provide different sketching means. One stage is used to create global shapes, and the other one is responsible for adding local details. Our experiment shows that this two-stage pipeline can well support the accurate control of global shapes and the generation of local details. To speed up the interactive modeling process and further enhance the generation of local details, we introduce advanced implicit-based neural networks to our pipeline. And we also constructed a large dataset to our implicit neural networks to learn the strong prior knowledge of animal-morphic heads. As you can see from the figure on the upper right, compared with FiberMesh, which is only based on surface optimization, our result looks more natural due to the introduction of prior knowledge of the implicit neural network. Based on the decompose of the pipeline, Our system provides two stages for mesh modeling: coarse shape sketching stage and geometric detail crafting stage. Here is our workflow. Now we use some examples to show the workflow of our system.
In stage 1, users start this stage by drawing a closed curve on the sketchpad for depicting a desired animal morphic head profile contour. Our system will then immediately generate a smoothed shape as an initial animal morphic head mesh through interpolation. Then users can use the provided extrusion tool to model head components like ears and horns. Users can also use the Add Curve tool to add a 3D handle. Besides, users can use the Handle Deformation tool to adjust the global shape. Next, users can click the Surface Carving tool to switch to Stage 2. In Stage 2, users may intuitively carve organic surface details, such as eyes and noses. Our deep learning-driven backend will immediately generate expected surface details after users click the Inference hotkey.
In this section, we will introduce the back-end algorithm for our interactive sketch-based modeling system. In the coarse mesh modeling stage, as seen in the left figure, given 3D curves drawn by users as input, our system generates an initial mesh M0 through surface optimization and predicts a corresponding voxel-aligned implicit field from the 3D curves. Then, the initial mesh M0 is deformed with the guidance of the voxel-aligned occupancy field. After that, a coarse mesh M1 is generated. Here is a pipeline of our voxel-aligned implicit network. For more details about the voxel-aligned implicit network, please refer to our paper. In geometric detail crafting stage, once users draw detailed sketches on M1's surface, our system first renders the front and back depth map from the coarse mesh M1, and renders a 2D sketch from the 3D strokes. Then a normal map is predicted by an image-to-image translation network. Here we use Pixel-to-Pixel HD. Afterward, all these four images are taken as input for the pixel-aligned implicit learning module to predict a pixel-aligned occupancy field. Similarly, this occupancy field is used to guide the deformation of M1 to produce a more detailed mesh M2. Here is a pipeline of our pixel-aligned implicit network. For more details about the pixel-aligned implicit network, please refer to our paper. Now, let's take a look at the dynamic process of our algorithm.
In stage 1, given 3D curves drawn by users as input, our system generates an initial mesh M0 through surface optimization and predicts a corresponding voxel-aligned implicit field from the 3D curves. Then the initial mesh M0 is deformed with the guidance of the voxel-aligned implicit field. After that, a coarse animal morphic mesh M1 is generated. In stage 2, once users draw detailed sketches on M1's surface, our system first renders the front and back depth maps from the coarse mesh M1, and a 2D sketch from the 3D strokes. Then a normal map is predicted by an image-to-image translation network. Afterward, all these four images are taken as input for the pixel-aligned implicit learning module to predict a pixel-aligned occupancy field. Similarly, the learned pixel-aligned occupancy field is used to guide the deformation of M1 to produce a more detailed mesh M2.
Here is our dataset, 3D animal head, which is the largest animal morphic head dataset by far. Here are some representative models created using our system. It can be seen from this figure that our system supports users with limited knowledge in geometrical modeling to create anamorphic heads with diversified shapes and rich geometric details. Here are some representative models selected from the comparison study. Obviously, given a limited time, the participants can create more appealing shapes and vivid details with our system. Finally, let's see the results gallery.
The final is the gallery of some representative models created using our system by 15 amateur users. It can be seen that our system supports users with limited modeling knowledge to create animal morphic heads with diversified shapes and rich geometric details. Thank you for watching.